Good morning, everyone. I will present you some work we have done in the frame of ALARM project related to the selected detection of dust and ash cloud from hyperspectral and broadband sensor. Here is the outline of my presentation. I will show you the motivation, introduce SAC system and ALARM project, give you some information about geostationary and low Earth orbit products to detect dust and ash. And I will show you alert products as part of SAC's alarm early warning system and give you some outlook. So when there is some dust storm, for example, in Saharan desert, this can be a threat for the population and aviation. You can see in this illustration the case of the dust storm in March 2018, where a lot of dust was over Heraklion in Crete. You can see that the airport was closed, and yeah, that can impact the aviation. You can see this is in this illustration the impact on the engine, and so this is the rotor of an helicopter, but you can see that the dust can have a strong impact and a lot of maintain of the engine for the aircraft manufacturer. You know the ABOB, that can be a big threat for population and aviation. The example of Kuwait sandstorm in 2018. You can see this plane with the ABOB just behind. Another threat we want to address with our early warning system related to aviation. This is the risk of volcanic eruption. You can see on this famous image from the International Space Center from ISS. You can see the cloud from Sarychev in 2009, and also Raikoki eruption in 2019. That has a strong impact on aviation. And by the way, the eruption of Raikoki was really important with a lot of SO2, 1.4 teragram was emitted of SO2 in the atmosphere. But you probably remember or I've heard about this volcanic eruption of Pinatubo in 1991, where a lot of SO2 and ash was emitted in Indonesia. You can see this photo taken from the east side of Clark Air Base. So basically 15 to 20 teragram of SO2 was emitted to an altitude of about more than 40 kilometers. You can see the impact of this plane, this McDonnell Douglas DC-10, that could not you cannot move this plane because all the ash that there is over. You can see the strong impact of Mount Pinatubo eruption that can have in aviation. So if there is some thermodynamic condition, the ash can melt, and if the plane go higher with lower temperature, then the ash can freeze, and that can stop the engine. That's what happened for a plane that was flying to Moscow during this Pinatubo eruption, and one of the engines stopped, but fortunately they managed to restart it. So you can see the big threat that can be for the aviation. You remember Eyjafjallajökull eruption in 2010 and the massive impact for this small eruption that the European airspace had. In this pirate map, you can see the frequent and occasional ash and sulfur producing eruption and the impact on air traffic. So that's mainly all around the the ring of fire. You can see the strong impact that can take place. It's not really well known, but the SO2 can also be a big problem for aviation, mainly due to sulfidation. There is different type of sulfidation. You can see on this illustration, and you can find more detail in the paper, the proceeding of César Innovation Day in 2020 that we published, mainly in the frame of this OPAS Engage KTN project. We provide SO2 from tropomy, and we give attention to the impact of sulfidation and look at it. You can see that for different temperatures, there is different kinds, some solid diffusion process, also some corrosion fatigue that can take place if you have a long SO2 contamination and a flight through a long period through an SO2 cloud. So that's a risk for aviation. In this map from Clarkson and Simpson 2020, so on the x-axis, you can see the ash and dust concentration. On the y-axis, this is the duration of engine exposure. And you can see in green line, dash line, and orange and red, this is the threshold that are using the VAC to determine the impact of ash contamination, so the concentration, so 0.2, 2, and 20 milligram per cube meter. You can see also the dashed line in blue that show you basically the impact for the different events, the regions of deterioration in safety margins. So here in purple, you can see possible and probable deterioration for the engine. In the ellipse represents some different events, volcanic ash, but also a sandstorm with dust. You can see that for some of the cases reported that there is an impact for the engine. And you can see that in a stripe in yellow, where there is a possible risk of a problem for the engine and where that requires some maintenance for the aircraft manufacturer. So you can really see the impact of ash and dust. So this is why, since 2009, ESA founded SACS projects, the Support to Aviation Control Service, and this collaboration between BIRA, that is leading this system, also with University Free of Brussels and CNES, KNMI, DLR, that was the main partner, and also NILU and FMI that provide the products that are used. And you can see the provider of data, ESA, EUMETSAT, and NASA. So we have a web-based service that can be used to see a near real-time image from different sensors. Mainly, at the moment, we use in this platform hyperspectral sensor in the UV and infrared with different overpass. You can see at different time of the day and the night, depending on where you are looking at the displacement of the natural hazard cloud. And the idea is to get all this data with different time delivery from 45 minutes, thanks to the very fast delivery over Scandinavia and Alaska, up to 3 hours. And then we get this data and we look at the risk and the possible notification of volcanic dust, smoke, and then we send it to the users, for example, the Volcanic Ash Advisory Center, the observatory, research institution, the pilots, airline, and scientists. From 2016 to 2019, SAC system has been upgraded in the frame of UNADIX project. It was a big project with 21 partners. The idea was to look at different kind of aspect related to natural airborne hazard. BIRA and SAC system was the base of the early warning system of this prototype work that has been done in UNADIX. And the idea was also to look at assimilation and ensemble modeling, and a lot of nice work has been done. We also look at the source, description of the source, alert product from ground-based network like EarlyNet has been developed in the frame of UNADIX. And we use different kind of information as part of the early warning system. And the idea, also VONA message from the observatory. And the idea was to combine all this information to create email notification, near real-time image, and data file transfer. As an example, I show you the notification sent by SAC system for the eruption, the paroxysm, for example, of Etna on the 28th of February. So we provide key information. There's also a link to a dedicated web page. You can find on the near real-time image on the SAC's web interface. And then in the notification, we send a link to a dedicated web page where you can have this key information, these tailored images that shows the location of the SO2 cloud. You can see also there is a link to Google Earth image. You can look at the SO2 cloud, but also the ash cloud, the absorbing index from Etna eruption. And there is also a link to the SO2 NCAP file, so that's the NetCDF alert product that the users can get in near real time after an observation. So in this NetCDF file alert product, so this is a NetCDF data alert product that is provided in a homogenized format. You can get the whole data of the sensor, but also the alert pixel, the level of severity that depend, for example, for the SO2 notification on the mass loading. You can look at the impacted flight level with SO2 contamination. We provide the extended plume, also surface and mass loading, gridded data that can be really useful for dispersion modeling. There is also information about the contour, the source, traceability of the event with the start and the end, and link to other image from different other platforms that is given in this NetCDF file. As an example, I show you for the Saharan subsoil dust storm in 2018, spring 2018, using OMPS UV perspectral sensor. We can detect the aerosol absorbing index and create some alert product. You can see on top image, that's all the data observation, then down all the dust alert pixel. Just under, you can see the completion of the aerosol dust plume, and then down the example of the contour. So this is shown using HDF viewer, and then you can have a look, take a quick look what the data look like. You can see the different fields that are provided. So in the frame of alert projects, we keep developing early warning system. We extended to space weather, for example, the impact on aviation of the radiation that can pose a problem to the avionics. We also look at greenfly with environmental hotspot, and we are developing the same kind of alert product. We are also making some research, exploratory research to detect severe weather, and especially small scale convective cell development, like for deep convection with a size of few kilometers that are not well forecast by a numerical weather model. And the idea is to use GNSS data of water vapor and to create obtain some precursor of the initiation of deep convection and to provide information to airports. So we focus on 2 airports, Milano and Brussels, to look at development of severe weather. And then we also have a part of it that is dedicated to smoke, dust, ash, and SO2. And the idea is to provide information to the stakeholder, and this is a partenariat with 6 different partners. BIRA, this is led by the University Carlos III of Madrid. Satavia and CIMOP are companies that are working inside this project. There is also the University of Padova that is doing the development of a network of ground-based stations for severe weather, and DLR that is providing the products related to environmental hotspots. So I will only focus on the dust and ash alert product related to natural airborne hazard, and we look at low Earth orbit and geostationary product to detect this natural airborne hazard. As a part of FENADIX project, we develop this kind of product. You can take a look more in detail looking at this presentation. Mainly there is UV and infrared low Earth orbit sensor that give us some selective detection of SO2, ash, and also dust. So that's dust optical depth from YASI. There is also the product from Semery, only over Europe, that we use to detect ash and the height of ash. So this is what we call the selective detection. You can see an example of YASI. During the hurricane of Ophelia, you can see the selective detection of dust. You can see from OMPS, you don't have a selective detection. You have this absorbing index. And then using a match in space and time between YASI and OMPS, we can use YASI data as a trigger of detection of alert pixel related to dust using OMPS data. It's what we call the triggered detection from different instruments. So in the frame of OPAS engaged KTN project, we developed the SO2 height from tropomy that I mentioned before. You can see for Raikoki eruption, the SO2 on the left, then on the right, the SO2 height that we developed. You can see in red dash, this was the trajectory of the flight GL5T that actually through the cloud. Even the Anchorage VAC mentioned that they could fly over 14 kilometers. This flight actually flew for about 1 hour through the SO2 and ash cloud with a value of SO2 over 50 Dobson unit. So you can see in the cross in blue, this is the height of the SO2 measured by tropomy. In the line, this is the SO2 column measured by tropomy, and you can see the trajectory at 14 kilometers and this 1 hour exposure. In the frame of alarm, we want to keep developing this trigger approach. So for other aerosol index measurement from the other UV hyperspectral sensor. We also want to apply this to MODIS for volcanic ash and dust to have to detect precisely the pixel with AOD in MODIS data related to dust or ash. And the idea was also to detect to use geostationary instruments, the 2 Severi and the 2 GOS and Himawari, to use it and to observe using RGB composite and to use the trigger approach. That was the first idea we had. But finally, we realized that we could try to do some selective detection, and I will come to that in the next slide. So using YASI, you can see that we can have classification of spectral signature from sound and from volcanic ash. And basically, we use this discrimination between mineral dust and ash from YASI, and to implement that in the SAX system. You can see in green, this is a mineral dust detected by YASI, and in red and yellow color, this is the ash for this Peway Cordon Cone eruption that took place in June 2011. So using this trigger approach with the dust flag from YASI, we can obtain in the MODIS data detection of the alert pixel and also a completed cloud of dust from the AOD from MODIS. You can see this comparison between YASI and MODIS with a very good agreement with the observation of the dust. You can see the alert pixel and the completed dust cloud, and as an example, what we provide in the NetCDF alert product. So that can be of interest for people who are doing some dispersion modeling of dust. So in the frame of alarm, we want to develop, use the geostationary instrument, the GeoRing, to have a global coverage using initially the RGB composite of ash and dust. You can see that the channel used by Gauss, Severi, and Imawari are really close. You can see using the linear combination in the red that cloud optical thickness can be obtained, in the green water cloud and also SO2 plume, and in the blue warm cloud and warm surface. So basically the RGB composites are very useful tool, powerful tool that can give a lot of information. You know that here there is the SO2 cloud, and then with your eyes you can see it and detect it. Of course, you can see also over Africa that the emissivity of the surface can provide also some green color. So this can be a problem if you implement an early warning system to use this product, because you can have some false detection, and of course the idea was to combine this with selective detection and to make some trigger approach. But at the end, looking at the data, we saw that it could be great to implement a direct selective detection, and that's what have been done in the frame of alarm. So using the covariance-based retrieval algorithm called COBRA, it's possible to implement some index of spectral significancy of SO2. So you can see this paper from Oliven Claris in 2013, and also the current paper of Nicolas Theys on ACP. You can have more information about this COBRA technique. You can see that the SO2 is index can provide a very selective detection of SO2, and that's really interesting to be used in our early warning system. So you can see that this algorithm can also be applied for the ash. You can see in blue the ash detected, and in red the SO2 detected by Severi. So that was on the end of February in 2021, the example of the notification that I provided before. Looking at Grimsvötn eruption in 2011, that's a really interesting case, because the SO2 cloud and the ash cloud actually was emitted at different altitude. The ash was going in the lower altitude in the south of Iceland, and the SO2 was flew on the north of Iceland. You can see in the RGB composite that we cannot really observe where the SO2 and the ash, you can really take a look deeply and see, detect where is the ash and where is the SO2, but it cannot really be used in an early warning system. You can see on the left, this is the SO2 and ash index that we developed at Bira. On the right, that is the ash detection and SO2 detection from Niazi that are used by SAC system. You can see that there is a very good agreement. If we look at the animation now, you can see that the SO2 is detected and go to the north, and the ash go to the south. So the interest of using Severi, you can see that the high temporal resolution is very powerful and interesting to be used in an early warning system. We did the same approach for the dust. You can see during this dust event that bring sun over Europe, you can see the detection that we obtain using Severi and that we plan to use in SAC system. Of course, the spectral signature of ash and dust is really close using the broadband approach, and I don't think we can cope and make selective detection of dust and ash, but we can detect the aerosols generally and identify the location with a really high temporal resolution. So to conclude, the combined use of low Earth orbit and geostationary data is really promising. We can use the trigger approach, but there is probably difficulty that can take place with frequent false alerts in a near real-time system. This is why we decided to use the Cobra analysis to make some selective detection of SO2, ash, and dust, and we find it really interesting, and this bring nice results. We plan to improve our algorithm and to use it as part of a SAC system to make some notification. For the moment, this has only been applied to Severi, but we plan to use it also for the GOES, so AIB and HIE instrument on Imawari for the next, that's the next step. You can see that thanks to Cobra analysis, this is possible to obtain a good detection in SO2 height. So this paper is currently in review in ACP about the SO2. So you can see that with a new approach, a new algorithm. So on this map on the right, you can see the pixel size. So you can see the pixel size, and you can see on the x-axis and on the y-axis the SO2 column detection. Basically, that gives you the limit of detection of the instrument. You can see that Yazi and Tropomi that are used by SACs at the moment provide very good results. But with the new algorithm, we can go to improve with an order of magnitude of the sensitivity and the detection limit of SO2. So that's what we plan to do in the future. We will provide to the interested person the aerosol index from MODIS and Tropomi, and we plan in the future to link that with e-profile data. We currently have near real-time access to all the data over Europe from the ceilometer, and this is something we plan to do for the next year. We also plan to link with EarlyNet data when we get them in near real time. We plan to provide our warning NECDF alert product to SDS-WAS, and this will be great to make it available through the modeler of that's part of SDS-WAS, and to make a forecast using our alert product. And finally, we want to make some SWIM notification service dedicated to aviation stakeholders. That is part of CESAR. So the SWIM, this is a system-wide information management. This brings data available for stakeholders in different formats. In the frame of OPAS project, we currently develop a notification service for the SO2 height, and we hope to develop that for other products as the one developed in Alarm. Thank you for your attention. You can take a look on Alarm project. We make a post about Cumbre Vieja eruption, And so yeah, take a look at it. So I hope my presentation bring you some light in this dust cloud, and hopefully you will contact us if you are interested to take a look to our products. Have a nice day.